So in order to define what is a differentiable manifold, we need first to say what is a topological manifold. And first of these, before this, what is a topological space? Topological space is a couple X Ni, when Ni is called topology. Ni is a family of subsets of X satisfying the following properties. Capital X and vacuum and the empty set belongs to the topology. A countable union of subsets of X or countable union of sets of the topology belongs to the topology. A finite intersection of elements of the topology belongs to the topology. A neighborhood UP of a given point P is actually a subset of X, such that it contains an open set U containing P. Open sets are the name we give to the elements of the topology. Open sets. Now let's have two topological spaces, X Ni and Y omega. A map phi is called to be continuous between these topological spaces if for each open set A of the codomain topological space, the counter image via phi is an open set of the domain topological space. We say that the topological space satisfies the T2 property, or being Hausdorff, or it's separable also. Is also said separable if for each pair of point X and Y of the topological spaces there exists two neighborhoods of one of X and one of Y which do not intersect. A covering of the topological space, a covering, is a family of subsets of X such that the union contains the whole space X, a covering. And if all these sets composing the covering are open sets, then it's called open covering. So a topological manifold is a topological space having an open covering, capital U, equal to Ui, such that each Ui is homeomorphic to a subset of Rn, and the dimension of the topological manifold is actually n. So a topological manifold of dimension n is a topological space having an open covering U, capital U, such that each Ui is homeomorphic to an open set of Rn. An homeomorphism between topological spaces is actually a map which is continuous with its inverse. So for each Ui, there exists a homomorphism phi, which is an homomorphism on the image. So from Ui into phi Ui, and is an homomorphism between topological spaces. Now, given a covering and a set of homomorphisms, the couple Ui phi is called chart. And the set of all charts by let I running inside the elements of the covering is called an atlas. An example of topological manifold can be Rn is trivially a topological manifold. A vector space, when we pick up a basis, let's assume that the vector space is finite dimensional, and let's EI be a basis. Then the map phi, which maps V into Rm, induces a topology on the vector space. So a basis pickups n reals, defining what a vector is in that basis, what is the representation of the vector in that basis. Another example is the n-sphere. For example, the n-sphere is the set of points x1, xn, such that x1 square plus xn square is equal to 1. We can construct some a covering ui plus minus, where ui plus is equal blah, 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 x1 xi greater than 0, ui minus is equal to x belonging to Sn such that xi is less than 0. And we can build this homomorphism phi I plus minus goes to ui, from ui plus minus into 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 some sets of Rn. For example, if Q belongs to U plus minus I, then phi U plus minus I is equal to x1 xi minus 1 xi plus 1 blah, 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 x. So it maps any spheres into disks of Rn. And it's easy to see that the set of all these ui plus minus phi I plus minus forms an atlas for the sphere. Now we are almost ready to define what a differentiable manifold is. So let x be a topological manifold, ui phi I be an atlas for the topological manifold. Assume that there is a ui and uj with no empty intersection, and set uij equal ui intersecting uj. Now this uij can be mapped in two ways, via the map phi I or the map phi j. So let's call phi I of uij equal to bij, and phi j of uji, which is equal to uij, equal to bji. Okay. We can obviously build the map phi I composite phi j to the minus 1, which maps bji into Rn. Okay, and we can ask ourselves, because f phi I composite phi minus 1j, which we call phi ij, because these phi ij are real valued functions of several real variables, we can ask ourselves if these maps are differentiable. So a differentiable manifold of class Ck is a topological manifold where the chart-changing phi ij are Ck function, are differentiable functions of class K. Now, if we have got an atlas, consider another chart V psi. Assume that V intersects some ui. For example, assume that V intersects ui. Okay. Now we say that V psi is compatible with the differentiable structure of the manifold, just in case the maps phi I composite psi minus 1 and psi composite phi I to minus 1 are of class Ck for each phi I such that ui intersects V. If this holds, then V psi is compatible with the differentiable structure of the manifold. If we include inside an atlas all the charts which are compatible with the differentiable structure of the manifold, then we obtain what is called a maximal atlas. So a differentiable structure is a manifold with a maximal atlas of class Ck. Differentiable structure of class Ck is a manifold of class Ck with a maximal atlas. Now, one of the next thing one can do is to consider functions, differentiable functions between differentiable manifolds. But first of all, we have to have a clue of what is a composition. So consider four spaces A, B, C, and D, with F, which goes from A to B, and G, which goes from C to D, but C is contained in B. Then the composition G composite F is nothing more than a map which goes from A intersecting F to the minus 1 of C into D. This is the composition. So we must be careful about what is the domain of the definition of the composition map. Now let M and N be two differentiable manifolds with two coverings, M UI Phi and N with Vj Pj. We say that a map F from M to N is regular of class K if it is continuous in the topological sense, and if for each pair of charts U phi and V psi such that U intersecting F, capital F to the minus 1 of V is not empty, then the map psi composite capital F to the minus 1 composite phi to the minus psi composite capital F composite phi to the minus 1 is of class CK, and we say that F belongs to CKMN. It will be called smooth in case K is equal to infinity. Now, the property of being differentiable regular of class K for a given function is actually a property independent of the choice of the charts. For example, if we include inside the atlas of M another chart, let's say W alpha, and we include another chart in N, in the topology in the atlas of N, a chart called zeta beta, and such that, for example, W intersecting F to the minus 1 of zeta is not empty, then we can construct the function beta composite F composite alpha to the minus 1. Now let us consider other two charts, one for M and one for N. A chart for M denoted by U phi, and a chart for N denoted by V psi, in the hypothesis that the chart zeta psi, the zeta beta, is compatible with the differentiable structure of N, and the case W alpha is compatible with the differentiable structure of M, we can always consider the map beta composite psi minus 1 composite psi composite F capital F composite phi to the minus 1 composite phi composite alpha to the minus 1. But because this is just the composition of differentiable maps, we obtain also differentiable maps. So the differentiable property of a given function between two differentiable manifolds is independent from the fact that we add to the basis manifold, domain and codomain manifolds, other charts compatible with their differentiable structure. Furthermore, let F and G be two K regular functions, F from M to N and G from N to X, then the composition G composed F is also a K-regular function, of class Ck from M to X. Okay, now two manifolds. This means that differentiable functions between manifolds can be viewed as morphisms, and we obtain the so-called category of differentiable manifolds whose morphisms are actually differentiable regular, K-regular maps between manifolds. Furthermore, if we have two manifolds, we say that they are diffeomorphic if there exist two maps G and F, F from M to N, and G from N to M, such that F composed G, G composed F is the identity of M, and F composed G is the identity of N. They are diffeomorphic. If we restrict their tension to the differentiable manifolds which are diffeomorphic one to each other, then we obtain a groupoid, or actually a category where all the morphisms are invertible. So let's say a groupoid of diffeomorphic manifolds. Okay. Now, from between all the differentiable maps, regular K-regular maps between topological differentiable manifolds, one of the most important are actually the real valued K-regular functions. K-regular function regular. The space of K-regular real valued functions is denoted with CKR or CKM, where M is the domain of the real valued functions and is a manifold. An important concept is the support of real valued functions. A support is the closure. Support of the function f is the closure of the set of all the points where the function does not vanish. The closure of this set is the support. Now, a construction, a tough construction, but not so tough, but let's say useful in some sense, construction makes possible to build constant functions equal to 1 in the neighborhood of any given point of a given manifold M. Support compact support function equal to 1 in any neighborhood. Deletions and translation make possible to construct functions, constant function equal to 1 in any neighborhood of any point of a given manifold M. So this property, this thing makes possible, it's much easier, it's obtains its maximum, this construction obtains its maximum useful, it's very useful. It's very useful in the case in which the manifold is satisfies the second countable axiom, the second countability axiom. So if its topology admits finite basis, a countable basis. Well, so a theorem holds, and this theorem is the following. Let's assume that UI, capital U, is a open covering of a differentiable manifold M satisfying the second countability axiom. Then there exist some maps, real valued maps, rho I from M to R, with support contained in UI, such that for each point P there exists a neighborhood W which intersects just a finite number of these CI supports of the rho I. Furthermore, the sum over I of this rho I is equal to E to 1. These rho I are called a partition of the unity for the covering UI. Really interesting because, for example, if we have a function f, real valued function f, we can construct this support function, this function fi, by multiplying f with rho I. Those are functions with support contained in UI, and f is obviously equal to the sum of this fi. So we have localized f as the sum of a function with support inside the open sets defining the covering. Another notion which is important for for example, the algebraic formulation of tangent vector spaces to a manifold is the notion of germs. So by definition we say that a smooth function defined in a neighborhood of a point P belonging to M is a couple FU, where U is a neighborhood of P and F is a smooth map defined on U. Okay. Now we say that two smooth functions defining a neighborhood of U are equivalent if there exists a neighborhood W of P such that the restriction of F to W is equal to the restriction of G to W. The quotient space of smooth functions defined in a neighborhood of a point P with respect to this equivalence relation is called the space of germs of the function of smooth functions at the point P. Now we can introduce what is called the tangent space to a manifold. There are two ways of defining this. First one is geometrical, the second is algebraic. For the geometrical part, we must introduce what is a curve over a manifold. So let's say we have a k-regular manifold. A curve is a k-regular map from a subset I of the reals into the manifold M. And we also say that if 0 belongs to I, and for example gamma of 0 is equal to P, we say that gamma is originating at the point P. So let's have two curves originating at the point P, gamma and alpha, from I to M, from J to M. Now let U phi be a chart defined in a neighborhood of the point P where the curves are originating. Then there must exist two neighborhoods, there must exist two subsets I prime and J prime of I and J respectively, such that the restriction of gamma to I prime is contained entirely in U, and the restriction of alpha to J prime is entirely contained in U. Okay, so we have these two curves, these two restrictions contained in U. Now, by composing these maps with the homomorphism phi, we obtain two curves O in Rn. Supposing M is the dimension of the manifold M, capital M, we obtain two curves. X is equal to phi composite gamma, and y is equal to phi composite alpha. Now these are curves, as we ever said, and the derivative and if the derivative with respect to t computed in 0 of x is equal to the derivative with respect to t of y computed in 0, then we say that the curves alpha and gamma are tangent to the point P. Okay, but the tangent property of curves is an equivalence relation. So we can construct actually the set of equivalence classes. So for example, if omega P is the set of all curves originating at P, we can construct the equivalence classes of omega P with respect to the relation of being tangent. And the quotient space of omega P with respect to these equivalence classes will be called the tangent space to the manifold at the point P. Okay, now there's a natural abstraction for this space, natural abstraction of real vector space. For example, we can consider a map C from TMP into Rm, defined this as follows. For each equivalence class gamma, we associate the derivative of phi gamma computed at t equals 0. This is a natural identification. So it is actually a vector, a real vector space of dimension equal to the dimension of the manifold. Now, let F be a map from two manifolds M and N. Let gamma be a curve on M. Then F composite gamma must be a curve over N. An important property is that if two curves are tangent at the point P over M, then these two curves are mapped into two curves tangent into the point FP over N. So the tangential property of curves is mapped is preserved when we map a manifold M into a manifold N via a differentiable map F. This means that the equivalence classes of curves tangent to a point P is mapped also into a respective equivalence class of curves tangent to the point Fp. So if we define the composition map F star as the map which goes from omega p into omega of Fp, we can define the differential of the map F at the point P as that map which is defined by the composition and maps element of Tpm into element of Tfpn. Okay, so equivalence classes are mapped into other equivalence classes, and a vector is mapped into another vector. Differential. Now this differential will be easily computed if we introduce the algebraic formulation of tangent space to a manifold. To do this, let's consider first the space of germs of function Gp C infinity P of M. This has naturally structure of vector space. Naturally. Now, what is a derivation over the space of germs of smooth function at a given point P? Is a map from the space of is a smooth map from the germs of smooth function at a point P into the reals, satisfying this property: x of f plus g is equal to xf plus xg. X of lambda is equal to 0 if lambda is a real, and it satisfies also the Leibniz rule. So x of fg computed in P is equal to xf computed in P g plus fxg computed in P. Okay? It's a derivation. But it's easy to see that a derivation is a linear function. So the space of all derivations is actually a subspace of the dual space of the germs of smooth function at a given point P. And it's a subspace, particular subspace, which satisfies the Leibniz rule. Each element satisfies the Leibniz rule. It is to see that the sum of two derivations is a derivation, and the multiplication by a scalar is also a derivation. So the space of derivations is a vector space. Now, consider U be a subset of Rm. It's easy to see that the partial derivatives form a basis for the space of the derivation at the point P, dPu being P a point of U, U being a subset, open set of Rn. The partial derivatives form a basis for the space of derivations at the point P if U is an open set of Rn. M. This means that dup is isomorphic to Rm, okay, being the partial derivatives a basis for it. Now, by composing with homomorphisms, we can build, starting from the partial derivatives, we can build a basis for the space of derivations at a point P of a given differentiable manifold then. And one of the results we obtain is that the space of derivation at a given point P of a manifold M has dimension equal to the dimension of the manifold. The composition is easy to achieve because we can consider the derivatives, partial derivatives equal to xi. For example, the derivative with respect to the variable xi. We can consider the vector, we can construct the vector f star xi, which is the preimage of the partial derivative. But this vector is applied to a function f at a point q. For example, let u be a neighborhood of p, and let q be a point of u. Q is equal to f to the minus 1 of x1 xm for some m-able. Now, phi star xi of gq is actually equal to the partial derivative with respect to xi of g of fi to the minus 1 x1 xm computed into phi of q. In this way we obtain what a derivation. What is the corresponding derivation over the manifold at the point P corresponding related to the partial derivative with respect to xi. But there's also another important property of derivation, and that they are isomorphic to the tangent space to a point P of a manifold. How can we see this? Actually, consider a vector v belonging to the tangent space at the point P. This is an equivalence classes of curves. Let's assume that gamma is the representative of this equivalence class. Then we can build a derivation in this as follows. Zeta of v applied to f is equal to the derivative with respect to t of f gamma computed in t equals 0. It's easy to see that this is a derivation, and the map zeta from tmp into the space of derivation dpm is a bijection. This can be proved is a bijection if defined in this sense. So the directional derivatives form this are the space, all directional derivatives form the space of all derivations, and the space of these derivations is isomorphic to the tangent space to a given manifold at the point P. Obviously we have to assume that f is, in this case, a smooth function defined in a neighborhood of a point P. Okay, now if we want to go further, we can, just to finish, F is, in the case F is a map between M and N, and it's a C-regular map. We want to say what is its differential in the algebraic formulation. For example, it's easy to see that F induces a map F star which goes from C infinity n into C infinity m, being C infinity n space of smooth function over m over n, and C infinity m the space of smooth function over m. It's easy to see, if F belongs to C infinity m, then F composite capital F belongs to C infinity m. So F star is equal, F star of F is equal to F composite capital F. Nothing more easy. Now the differential of capital F at the point P, when computed on a vector x, now we have identified the derivations and tangent vectors, so x can be viewed as a derivation of tangent vector as well. When applied to a function f, because now it's a derivation, we see it as a derivation, when applied to a function f at the point P, we obtain x of f x computed over f star of small f, and this is the derivation, and this is the differential of the map f at the point P.